Bismillahirrahmanirrahim. Starting with the name of Allah. So we will have to discuss the study of optical properties of molybdenum disulphide MoS2 thin films. Okay, my name is Hammad Shaukat and I am presenting the study of optical properties of MoS2 thin films. So first of all, the layout we will discuss in introduction. We will discuss low-dimensional systems, density of states, energy band gap, surface to volume ratio, quantum confinement effect, graphene, then molybdenum disulphide MoS2. Then secondly, we discuss about the growth of MoS2. In that, we will discuss the temperature mapping, RCA cleaning, thermal vaporization of MoO3 precursor, and sulfurization of MoO3 precursor. Okay, and last we will discuss our characterization, which are the literature characterizations of optical analysis of growth films like optical images, SEM and AFM. And lastly, we will discuss about the summary and conclusions and future framework. So first of all, low dimensional systems based on the dimensions of the material. So in that we have naturally occurring materials or 3D materials in which all dimensions are greater than 100 nanometer, and those materials are known as bulk materials. In low dimension systems, we have 2D materials, we have 1D materials, and we have 0D materials. Okay, 2D materials in which one dimension is greater less than 100 nanometer, like this nanosheet, and in 1D, at least two dimensions are less than 100 nanometer, like nanowire, and all dimensions are less than 100 nanometers are quantum dots, like okay in 0D material. So move on towards the density of states. So density of states also changes, as you can see, from 3D to 2D. As we move from dimensionless systems, you can see the density of states varies. The graph you can see in 3D, the graph shows constant behavior after some value, and in 2D you can see it's stepping up like graph, and you can see in 1D the graph changes, and in 0D you can see graph like a delta function. Okay, so the density of states also changes as you uh, change the dimensions of a material, okay, from 3D to 0D. Next thing is the energy band gap. Energy band gap also got increased as you go to the dimensionless systems. Like you can see, for 3D materials, the band gap is low. Okay, band gap is basically the band gap between the valence and the conduction band. So you can see now for the 2D materials, the band gap got more increased, and for the quantum dots, the band gap is more increased. And it's also depend upon the size of the quantum dot. If your quantum dot size is 6 nanometer, okay, so the energy band gap is little bit small, and as you go more smaller in size in quantum dot, like as you move like 4 nanometer, 4 millimeter, or up to 2 millimeter quantum dot, so you can see the band gap got increased. Okay, so the band gap got increased as you move on from high dimension to low dimension, and it also got increased in quantum dot sizes. Smaller the quantum dot, the greater is the energy band gap. Okay, now move on towards the surface to volume ratio, and surface to volume ratio also got increased because 3D system, you know that all dimensions are greater than 100 nanometer, only their faces are in touch, and once you go into small dimension like 2D, then more surface to volume ratio takes part into that, and once you got a single like this cube, in which you can see that surface to volume ratio is 6. Okay, means more sides, more area going take part into the reaction or anything else. So surface to volume ratio is inversely proportional to the characteristic size or radius. You can see the greater the size, the smaller is the surface to volume ratio. The smaller the size, the greater will be the surface to volume ratio. Okay, As dimension decreases, you can see that the surface area becomes a larger fraction of total material. Okay, so thus increases the surface to volume ratio. Now move on towards the next effect, which is the quantum confinement effect. So degree of quantum confinement also got increased as you move from high dimension to low dimension. So let's check. You can see that for the 3D materials, because all dimensions are greater than 100 nanometer, so number of free dimensions, all dimensions are free. Your electron will move in all three dimensions, either x, y, or z. So if electron is moving in all dimensions, so there is no confinement. So there is zero confinement in 3D. And in 2D, you can see, because now your material electron has to be moved into only two dimensions, because one dimension is less than 100 nanometer. So the quantum confinement is now 1. And in 1D material, now your electron is only supposed to move in one dimension, because other two dimensions are less than 100 nanometers. So the quantum confinement is 2. And for the 0D, similar process, because your electron has nowhere has to be moved. So all the three dimensions is confined now. Okay, so this is the 0D effect. So your illustration is given below. You can see this is for 3D, electron is moving in all three dimensions, and 2D electrons is moving in xy direction, and in 1D only in x direction, and 0D now your electron is confined in a box. Okay. Okay, now move on towards the graphene. What is graphene? Basically, this is the best studied 2D system. Okay, material you can say, and its freestanding atomic layer of carbon atom means you can remove the layer of the graphene from any substrate easily. Okay, and it has a high carrier mobility. You can say up to 2 lakh centimeter square per volt second. Okay, and high current density, approximately 10 is power 12 per centimeter square, and high electrical conductivity, approximately equals to 10 is per 8 servant per meter. Okay, and high thermal conductivity, which is 5000 watt per millikelvin. Okay, and expectational mechanical strength, which is 335 newton per meter, and prominent material for fabrication of electronic devices, because it has very vast variety of applications, vast variety of the features, as we discussed: high carrier mobility, phase standing atomic layer, high current density, higher electrical conductivity, and higher thermal conductivity. Okay, so, so this is the properties of graphene specifically. But why we are not using graphene? We are using the MoS2. Okay, so there is some limitations of graphene, and the limitation is that, okay, let me show you here. Okay, so what's the limitation of graphene? Is basically it has zero energy band gap. As you can see, this is the EK diagram of graphene, and this is the conduction band, and this is the valence band. And you can see there is direct connection of valence band to conduction band. There is no band gap. So if there is no band gap in graphene, so we can only switch on the material, so all the electrons move towards the conduction band, but we cannot stop the process. We cannot switch off the reaction, you can say. Okay, because to stop there must be band gap. So in graphene there is no band gap. That's why this is one of the limitation of graphene. Now move on towards the transition metal dichalcogenides, TMDS. The chemical formula of TMD is basically MX2. M is basically represents the transition metal, and X represents the chalcogen atoms, which are 10 in series. As you can see, this is the periodic table. So group 4, group 5, group 4 and group 7, some elements are so called as the chalcogens. This is marked as this. You can see this titanate, zircon. Okay, these all mm, atoms are basically chalcogen atoms, and there are three transition metals. These are the transition metals: silicon, selenium, okay, and this. So these are the chalcogen atoms. So the combination of MX2 means transition atoms and dichalcogens means transition metal dichalcogenides, TMDCs. Now move on towards one of the TMDs, which is molybdenum disulphide MoS2, whereas MO is the transition metal. As I can see, MO is basically the transition metal, and S is basically the chalcogen atom, and S2. So it becomes a TMDs. MoS2 is a TMDs. So now discuss the properties of MoS2. So first of all, it has graphene-like properties. Okay, combines high electrical conductivity with excellent mechanical strength. It has tunable energy band gap. Okay, tunable energy band gap, because as you can see, in bulk it has energy band gap of 1.2 ev, and in monolayer it has 1.8 evs. So you can see in bulk the energy band gap is low, but as you move from high dimension to low dimension, so your band gap got increased 1.8 electron volt. And the next property is low cost production. This is abundant in nature, okay, and more cost effective than graphene and other 2D materials. Strong photoluminescence, ideal for optoelectronic devices due to its efficient light emission. And lastly, two-dimensional material, strong in plane bounding, okay, and you can see that weak out of plane van der Waals forces enables its unique properties, okay. So these are basically the properties of MoS2. So it is basically strong in plane bonding, and there is weaker out van der Waals forces. So this is the diagram of MoS2. You can see this is the diagram for the monolayer of MoS2. You can see the valence band and conduction band, and the energy band gap is 1.8 ev. All the properties are same, and the only thing is that there is a band gap. So that's why we are using MoS2 instead of graphene. Now move on towards the formation of MoS2 molecules. You can see these are the two sulfur atoms which are connected with MO molecule with covalent bond. 2.41 angstrom is the bond length, and the formation of monolayer. How monolayer formed? This is, you can see, end to end connection of the MoS2 molecules formed. Formation of MoS2 monolayers. And how formation of bilayers formed? You can see the connection of monolayers with van der Waals weak interaction forms the bilayer. And how bulk crystal form? The connection of several bilayers with weak van der Waals forces forms the bulk crystal. Now move on towards the growth of MoS2 films. So first of all, the flowchart for the growth of MoS2 films. First of all, we have to perform the temperature mapping of course tube. Then we will discuss about the cleaning of substrate. This is our silicon substrate. And then the growth of oxide layer. You can see we growth an oxide layer on the surface of the silicon substrate. And then we have to grow of our MoS2 film on the substrate. This is you can see the molecules of MoS2 films on the substrate. After that, diffusion of MoO3 precursor, and this is how they diffuse, and conversion of MoO3 into the MoS2 during the process of sulfurization. Now your MoS2 is successfully on the glass silicon substrate. This is our results of temperature mapping inside the quartz tube. Okay, this is the distance and this is the temperature we take at 1130 degrees Celsius. Okay, we got peak value at 1058 degrees Celsius. So now move on towards the next RCA cleaning. So RCA cleaning is basically a very important cleaning method of a substrate to remove the contaminants. So for that, this is basically to remove the contaminants. So it consists of three steps. So in first step, you have to remove the organic contaminations. So for that, you have to use first beaker in which you have to take 50 ml of deionized water, which is poured with 10 ml of ammonia and 10 ml of hydrogen peroxide H2O2. Okay, and in second beaker you have to take 500 ml of deionized water, add it together with 10 ml of HF, okay, hydrofluoric acid, and in this beaker you have to stir for 15 minutes. In first beaker you have to stir for 10 minutes, and in second beaker you have to stir for 15 minutes, and in third beaker you have to take 50 ml of deionized water overpoured with 10 ml of hydrochloric acid HCl, and lastly 10 ml of hydrogen peroxide H2O2, and you have to stir for 10 minutes. After that, your substrate is successfully cleaned and it has zero contaminants on the silicon substrate. This is very crucial to remove all the contaminants from the silicon substrate. Now move on towards the growth of MoS2 film. So temperature region inside the quartz tube, as you can see, this is our quartz tube, and inside the tube furnace, which is 21.5 centimeter both ends outside, and we have a controller and power on off button. Now what you have to do, we first set temperature at 1130 Celsius, and these are the distance we get. At 9 centimeter we have a temperature which is less than 130 degrees Celsius, and at 62 centimeter we have a temperature 519 degrees Celsius, and at 63 centimeter we have a temperature of 920 degrees Celsius. We know that from literature that first of all your MoO3 precursor flows up to the silicon substrate at temperature around about 915 to that. So that's why we have to put our, you can see here, we have to put our MoO3 precursor in this boat, which is only 1 centimeter apart. There is a silicon substrate which is now cleaned and which is at distance 63 centimeter, and this is at temperature 920. So this is a very good temperature in which your only MoO3 precursor has to be pushed up to the on the silicon substrate, and this sulfur powder is placed at 9 centimeter. Here the temperature is less than 130 degrees Celsius, and temperature less than 130 degrees Celsius, your sulfur will not evaporate. First of all, we only need to evaporate this MoO3 precursor on the silicon substrate. So positioning of the precursors and sulfur in the ceramic pot, you can see this is our silicon substrate here, and here we have MoO3 precursor, and here which I mentioned we have the sulfur powder. Okay. Now positioning of ceramic pots for thermal vaporization of MoO3. As I mentioned you, we have to evaporate our MoO3 precursor. So for that you can see here we have the boards. We have sulfur in this boat which is at less than 130 degrees Celsius, and this is placed at these positions which I mentioned you before inside the quartz tube, and the distance between the silicon substrate and the MoO3 precursor is just 1 centimeter. Okay, and sulfur powder is placed at that temperature where it is not evaporate initially. We just has to evaporate first of all the MoO3 precursor. So that's temperature positions are ideal for this. Now what would happen now? You can see the process of thermal evaporation of MoO3, how it forms. So this is animations you can see. This is our MoO3 precursor and this is our silicon substrate, and we have to put our nitrogen gas externally. Now you can see what would happen. You can see now the precursors are now forming on the silicon substrate. Once it's successfully on the surface of the silicon substrate, what would have to do now? The next step is basically the sulfurization. For sulfurization, what we have to do now, our task is we have to evaporate our sulfur on the silicon substrate, which has already some MoO3 precursors on the surface. So for that we know that from literature that sulfur powder evaporates at temperature of greater than 130 degrees Celsius. So to increase the temperature, what we have to do, we have to push up the quartz tube from the side from the sulfur board and 17 centimeter inwards, so that now your sulfur powder got temperature greater than 130 degrees Celsius. Now see the animation which I told you. Now you can see this is 17 centimeter inward. Now the new positions and temperatures are mentioned. So after moving 17 centimeter inwards, now your silicon sulfur powder is now came at 26 centimeter, and here the temperature is 240 degrees Celsius. And we know that from literature, your sulfur powder evaporates at 240 degrees Celsius. Okay, and now again the boat containing the silicon substrate having MoO3 precursor on upside now got the position at 80 degrees Celsius, and it is at the temperature 1014, and this is very crucial temperature at which your molecules of sulfur and MoO3 combines and got chemical reaction, and after chemical reaction they form MoS2. Okay, so now see the process of sulfurization, how it formed. This is the illustration I mentioned you. So this is our MO3 because silicon substrate, and our second board having sulfur powder. This is our second ceramic board. Externally, we need the nitrogen gas to just push up the sulfur powder from one board to another board. This is how it works. Your sulfur powder goes up the slide of substrate of containing MoO3, and this is at temperature 1014 Celsius at 1014 degrees Celsius. From literature we know that the molecules of MoO3 diffuses on the silicon substrate with the sulfur to form MoS2, molybdenum disulphide. So this is the reactions formed after your all sulfur powder drops on the silicon substrate which already contains MoO3. So MoO3 react with the sulfur to form MoS2. Okay, so now your MoS2 film formed on the silicon substrate successfully. Now the growth of MoS2 films, growth parameter of MoS2 film. So these are the parameters. For oxide layer, it took 122 of total minutes. For the vaporization of MO3, it takes 15 minutes, and for sulfurization process, it took 25 minutes. And for the growth temperature, oxide layer forms at 1315 Celsius, and substrate during the vaporization of MO3, it process at 920 degrees Celsius. In the substrate during sulfurization, it is at temperature 1014 degrees Celsius. The quantity of precursor, we take the MoS2 powder in the boat, which is 13 milligram. As sulfur powder, we take 1 gram. Okay, and the flow rate of the carrier gas, we are using the nitrogen gas N2, and the gas pressure is 4 bar per second. Okay. And lastly, the distance of the substrate from MoO3 precursor is just 1 centimeter. Now these are the results, and optical microscope of MoS2 crystals formed. These are the optical images. First of all, you can see that the triangular shapes formed in all the optical microscope of MoS2 crystals. So the characteristic triangular shape of MoS2 flakes indicates of single layer or few layer structure. Okay, so these all are the optical microscope of MoS2 crystals from different papers, from different research articles, and in all, the MoS2 can be formed by CVD technique using MoO3 precursor, and these are the flakes of MoS2 formed, and the optical images shows that the triangular shape of MoS2, which basically indicates the single layer or few layer structure. Next is you can see that the uniformity. Okay, the images reveal the uniform of the flakes, suggesting consistent growth conditions. So as you can see in these pictures, you can see there are many triangles which are uniform. So here is more uniformly the flakes formed. So more growth, consistent growth conditions. So here where are less triangular shapes means there are less consistent growths. Next is basically the layer thickness. So you can see that the presence of different color in the images might indicates variation in the layer thickness, because you can see that the in this figure you can see this is you can see yellow type structure, yellow type color. This is basically the thick layer, and this is bulk layer, and this is you can see where there is no color. This is 20 mu micrometer images, and this is there is no there is multi-layer. Okay, mono-layer, sorry, there is no multi-layer because there is no dark color here, there is light color, so this is the mono layer. And you can see this is the dark most color, and this is the bulk layer, you can say, or you can say the sublimation. Okay, and lastly, the crystal size and density. The image can provide in these images basically provides the information about the size and density of the grown crystal. Okay, so by optical microscope we can easily visualize the size of the and density of the crystal. Okay, so here you can see we can measure the size of the crystal, and we can also measure the density. This is the 37 micrometer view. This is 50 micrometer view. These are the 2020 micrometer, and this is 95.32 micrometer view. Now move on towards the SEM characterizations of MoS2. These are the images which we take from different literature research articles. Okay, these are the SEM characterization. So from these results we obtain, first of all we see that the triangular morphology. Okay, the characteristics triangular shape of MoS2 flakes indicates the single layer of foliar structure. Okay, so you can see that there are MoS2 flakes. These are the triangular MoS2 flakes. You can see this basically shows the single layer or probably chances of the few layers means multi-layer, which is the bulk material. So SM also indicates the layer thickness. The presence of bilayer and monolayer region can be identified. Okay, bilayer means when two layers formed up down, and monolayer is a single layer. Okay, which is formed. You can see from this figure like this. This is multi-layer because there is no darkish. Here is the bulk layer. Bilayer, okay, and here is the sublimation. You can see this white. Next is the surface features. The same image can reveal surface roughness, okay, defects and grains boundaries. You can see it easily reveals the roughness how rough is your boundaries. Okay, so this is not rough and these are the rough boundaries. This is not rough. And lastly, the crystal quantity. The well-defined edges and smooth surface indicates high quality of MoS2 crystals. Okay, so you can see here the sharp and high quality MoS2 crystals formed. Okay, and smooth edges. So from these MSCM characterizations of MoS2, we can easily identify the crystal quantity, their layer thickness, and their triangular morphology. Okay. Now move on towards our last characterization, which is the AFM, atomic force microscopy. Okay, this is a powerful technique for nanoscale imaging. So these are the results, okay, which we take from different literatures. So from these results basically shows that the layered structure, okay, the step-like feature in image reveal the layered structure of MoS2. You can see this is our sphere and this is MoS2. So we are taking this region, this to this region. So there, so by AFM we can see that this has a layered structure because you can see here is the images the surface is low, but here is a peak of 0. Here is a distance up, which is 0.729 nanometers, and there is a spike up. So this means the surface is not uniform. The surface is layered structure. Okay. Next is the monolayer thickness. We can measure the monolayer thickness by using AFM. So the height profile confirms the presence of single layer of MoS2. So this basically peak the height of the presence of any single layer basically identifies the monolayer thickness of the MoS2. Basically the height identifies the thickness of the MoS2. Okay, and the next is basically the surface morphology. The surface morphology basically the image provides insights into the surface, rough and presence of defects. So surface morphology, this basically identifies the roughness and the presence of defects. Where there is no monolayer of MoS2 formed, we can easily identify, and where there is rough surface, we can also identify. So you can see this figure. So you can see distance from this to this we are taking, and there you can see roughness. So from figure you can see there is a spike. So this spike basically shows the here chances of either roughness or chances of some defects that form in the formation of MoS2. Okay, and implications for device performance. The quality of MoS2 layer as revealed by AFM. So only qualities of MoS2 film can be revealed by AFM. Okay, means if there is no defects, no roughness can be checked by AFM. If it correct, then this is moved for the device fabrications as revealed by AFM. Directly impacts the performance of the electronic and optoelectronic devices. This you can see distance we are taking from here to here, and here is a peak up, and suddenly peak down means there is either a defect or roughness. Then again peak up. So this is the quality of how MoS2 form. This is a quality of. So this AFM basically describes, reveals the quality of MoS2 layers on the silicon substrate. Okay, now move on towards the summary. So MoS2 films has been grown on silicon substrate by using this CVD technique. Initially, star-shaped MoS2 flakes are produced, which are interconnecting to neighboring flakes, forming thin film. And SM shows individual flakes and explain different color regions are actually having different density and size of the nucleation sites. And the conclusion is star-shaped flakes of monolayer of MoS2 has been achieved while the uniformity and coverage area of monolayer of MoS2 depends upon the size and distribution of MoO3 precursor on the surface of the substrate, and optical analysis provides confirmation of locally available of small patches of MoS2 films. MoS2 films of different thickness, monolayer, bilayer, or trilayer, or bulk, you can say, can develop by CVD techniques according to the applications. So future work is basically improve the quality and coverage area of MoS2 films. So for that we have to control over the flow rate of the carrier gas. We have to be post the position annealing under surface atmosphere, and second introduce some new techniques to diffuse uniformly small scale of MoO2 precursor to obtain uniform nucleation site on the surface of the substrate. So investigate MoS2 film for simple electronic devices like diodes and transistors. Okay, so thanks for watching. That's all for today's our presentation on the study of optical properties of molybdenum disulphide thin film, which is a 2D material. Okay, so that's all. Thanks for watching. Stay tuned with us. We'll upload more interesting lectures and videos according to these videos. So, if you have any question, any query, you can leave in the comment below. I will definitely answer your questions. Okay, and if you want this PPT presentation file, just leave your email below with the remarks that I want these slides. So definitely I will deliver it to you via email. Okay, so that's all for the study of the optical properties of molybdenum disulphide MoS2 thin films, okay, which is the 2D materials, and we successfully delivered all the layouts step by step in this video. Okay, so thanks for watching. Stay tuned with us. Till then, take care. Allah Hafiz.